picking up good vibrations.
Now time to have a look at some of the properties of the convolution. I already mentioned the commutative property. That basically means that taking the convolution of x and h is the same as taking the convolution of h and x. We can exchange the order. Then we have the associative property. That basically means that if we take the convolution of a signal with the sum of two signals, that's the same of taking the sum of the individual convolutions of x of the first signal and each of the two other signals. Finally, we have the distributive property, which means that if we want to compute the convolution of three signals, we can compute first the convolution of signal number 1 and signal number 2, and that the result, compute the convolution of the result with the third one, or compute first the convolution between the second and third signals, and only then compute the convolution with the first. Now we will look at a very, very important property. Is really instrumental. It states that the response of a linear time invariant system to an exponential input is an exponential input. The exponential must be considered from time minus infinity all the way to infinity for this to hold. For instance, we have seen some examples of computing convolutions between two exponentials that only start at 0. And then you don't have this property. It must be really the exponential from minus infinity until infinity. Moreover, although we consider first exponential this z to the power of n, this z to be real, z can also be a complex number for this fact to hold, and we can work with generality by considering z to be complex. Let us see why this is the case. Now it is more convenient now to write the convolution between h and x in such a way that h is fixed in the summation. So the summation from k equals minus infinity plus infinity of hk x of n minus k. Now x of n minus k is nothing more than z of n minus k. We can write z of n minus k as z of n times z of minus k. Now very important trick. Inside this summation, we get a term that does not depend on k, z of n. So we can take it out of the summation. By taking it out, we get the exponential that we're looking for, and what is left, the summation of k equals minus infinity of hk z minus k, is nothing more than a number. If z is real, it's a real number. If z is complex, it's a complex number, but it is a number. So we get, as a result, if we call this number capital H of z, we get capital H z times zn. So we start with z to the power of n, and we'd end up with z to the power of n times a number, a scalar. Here is an example where the input to an LTI system is an exponential input. We first compute convolution with a simple method and confirm that we obtain the same result with the method just described in the previous slide. The system represents a weighted moving average, which is non-causal. Now, if we simply replace x by alpha n, we'll get this expression. In factoring out alpha n, we get that the output is indeed an exponential alpha to the power of n multiplied by a constant. Now, here we just use very basic concepts, but we can also solve this with a method just explained in the previous slide, where basically we have to compute these constants with the formula given in the previous slide for capital H, and if we do that, we obtain exactly the same expression as we obtained with a simple method. The fact that we can consider complex exponentials, however, allows us to conclude another very important and instrumental fact. The response of a linear time invariant system to a cosine or sine input is a cosine or sine output multiplied by, it's a cosine or a sine, but multiplied by a constant with a phase shift. Let us now see why. We know that we can write a cosine as a real part of a complex exponential. And the real part can also be written as the complex exponential plus its complex conjugate over 2. so as a weighted sum of complex exponentials. We know that also that the output response to each of these exponential systems is also an exponential signal multiplied by this capital A H Z. But now Z is e to the power of j omega. It is the ratio of the exponential here, e to the power of j omega n. Therefore, due to linearity, we also know that the output response to a cosine will be a weighted sum of these two complex exponentials multiplied by h of e to the power of j omega and h e to the power of minus j omega. Now, an important fact that I will not mention here is that h of e to the power of j, that I will not prove here, it can be found in the lecture notes. Capital H of e to the power of j omega is the complex conjugate of capital H of e to the power of minus j omega. And so once we apply this weighted sum of complex exponentials, we get at the output also weighted sum, but now multiplied by capital H of e to the power of j omega and the second term that is associated with e to the power of minus j omega and multiplied by its complex conjugate. So capital H of e to the power of j omega complex conjugate. Now, if we compute this, if we call this complex number capital H, capital A e to the power of j gamma, we can group these two terms and say that the output is capital A cosine of omega n plus phi, the original phase of the input signal, plus gamma, which is the phase of this complex number capital H. Here is an example where we want to compute the response of an LTI system to a cosine. We know that from the previous slide this is also a cosine, but with different amplitude and phase. The amplitude and phase are the absolute value and the angle of this complex number capital H, and we have a formula for it. So if we apply the formula, we get the sum of a geometric series. There's a formula for that, 1 over 1 minus the ratio, and that is a complex number. If we compute that complex number, it will give us, it will have an amplitude or magnitude and a phase. The magnitude is 1.7011 and the phase is minus 0.9271. That means that if we apply cosine of 2 pi over 10 n at the input, the output will be 1.7011 cosine of 2 pi over 10 n plus the phase, which is minus 0.9271. Very, very important to compute capital H. We have to evaluate it at e to the power of j omega, where omega is the input frequency of the input signal, 2 pi over capital 10, over 10.